Thank you very much, Sasu. Good morning, ladies and gentlemen, both here in person in Helsinki and the one joining us from across the globe online. It is truly a pleasure for me as well to welcome you to IEEE Services Conference 2025. And I would like to thank the organizer for bringing us together and for this invitation. It is a privilege to stand before you, a gathering that for more than 2 decades has shaped the frontier of cloud, edge, AI, and very fabric of modern computing. We are meeting at a time when the world's digital infrastructure, not only being reimagined, is being redefined by the convergence of services, the rise of intelligent ecosystem, and a collective call for type of computing that is not only more powerful, but also is more sustainable, more secure, and more fair for everyone. As we enter the next era of information and communication services, overwork as scientists is no longer just technical. It is transformational. It is going to impact everyone's life. From the way that the hospital are going to deliver care, the way that governments are going to ensure equity, and to how industries are going to prepare themselves for the era of AI-driven economy. So today I'm going to talk about the expectation and future of services and the platforms that are going to deliver these services. But before I start, however, I would like to share with you that this year also, we are celebrating 100 years of innovation at Bell Labs, Nokia's global industry research arm. For a century now, Bell Lab has channeled the greatness of the researcher's mind into visionary technologies that are actually shaping the whole world economy. This is also a tribute to greatness of human intellect, regardless of where they are and which institute they belong to. And a humble reminder as well that technology and science is never an isolated thing. We are evolving this as a cumulative effect and progress. All that we achieve today builds on the realization of the one that came before us. Those that dared to challenge the limits and never wavered in the pursuit of proving what is actually possible. So Bell Labs is also where many technology that you deal with and you're using in your daily life have been born there. This includes transistor, foundational information theory, C++, UNEXT, and so on. I'm not going to read everything that is on the board. I'm sure this community really appreciates the impact this technology has had on the evolution of both computing and networking. Think of transistor. It was developed as a replacement of a vacuum tube, which was heavy, and that tiny device then later revolutionized the entire industry of electronics. So it starts with an engineering problem, but then you see the grand effect of it. Information theory, it was Claude Shannon that during the World War II actually was dealing with cryptography, and he started developing the fundamental of information theories. Neural network, Jan LeCun and Larry Jekyll developed convolutional neural network, a class of deep feed-forward artificial neural network. And pretty much across all the sessions that you see, there is no one that doesn't talk about AI. At Bell Labs, then carrying such a legacy, it's both an honor for us, but also a responsibility. We continuously remind ourselves that what we develop, it should have positive impact on the entire humanity. And we think forward, what will be the length of this impact? So I want to come to zoom into one of the technology that actually has inspired what I do today in my lab. I don't know if it's, yeah. Personally, I have been always fascinated by concept of operating system, and that's where I followed. Unix operating system aimed to create a simple, flexible, and interactive system for programmers to make best use of their computing resources. And it had to create the ability for multiple programs to come together and actually create a complex program. So I will not go to more detail of that. But it was modular, and it had the possibility of composing the bigger complex program. We now today, however, we are dealing with a situation that service-based businesses and architecture have extended to the opportunity to many, many actors across the globe. And think of this actor wanting to use the resources also that is available across the globe, both computing and networking. Can we make it easy for them to do so? So it is like almost stretching Unix across the globe for using the global heterogeneous resources that are available. So the question is, what is the operating system, or is it an operating system for this global heterogeneous multiplayer environment? Approaching this context, we also have to have, similar to Unix, we have to have the experience of a user in mind, the user that wants to actually compose these services, precisely the way that Unix was thinking about how the programmer are going to deal with computing. So our vision is UNEXT, intentionally rhymes with Unix because we continuously want to remind ourselves about the operating system design principle. It stands for Unified Networking Experience Technologies, and it addresses all the challenges that one needs to deal with to have this easy access for the resources for composing services into multi-actor environments. So let's take a closer look. But before that, you can ask yourself, is it a fancy play of the words? Is it just the momentum that we want to continue? We want to create a big problem that is going to keep us busy for a while? Yes, as Sasu mentioned, I have been always interested in complex systems, but for making them simple to use. So simplicity always is on my mind. But to see the reality that we are dealing with, all around us, the journey of digital transformation is still evolving. So we have Industry 5.0 and robotics. And there is that expectation that enhanced real-time control in a smart factory, for instance, could change the business model there and also create much more easy operation in these factories. At the same time, we want to guarantee ultra-low latency for the high reliability for the robotics. If you go to the use cases or the services that deal for the immersive AR, VR, we need to enable fluid, seamless experience, both for the end user, for example, adapting the stream of data toward the user context specifically, but also device capability that is able to carry that, and also network condition be taken into account. In radio network itself, if we look, real-time analytics and efficient data collections are essential, and we have team members working on them. But it is along together that collection of data and automation of data is really for using those data for reconfiguring a network when the condition is changing. And also both in radio and transport, in the future that we are looking at the capabilities of sensing with the same infrastructure. So both radio and also transport fiber under the sea could actually sense. That means it's collecting massive amounts of data. Where are these data going to be executed? How they are going to be transported? Which type of model we're going to use to predict real time? If under the sea, the fiber is sensing a turbulence, that means it could prevent a disaster, could alert for upcoming, for example, earthquake. That means how critical it is that we have this real-time processing of data. In all of this domain, in all of these 4 examples, and I could continue giving more examples as well, but in all of this example, you see actually there is a distributed execution environment, and there is a fusion of compute and network. There is a knowledge sharing across this different domain and among the actors there. We will come to that a little bit more in detail. But there is also the sensitive data in place that you should have trust mechanism in place to actually allow the actors to share the data between each other. There is a co-optimization of network and application that is needed. And of course, automatic service creation becomes fundamentally critical in this space because you can never know what new requirement you might have and which new services you might need. So you see, this is not really a hypothetical future that we are perceiving. This is actually the path that we are already on. But we are so concerned by addressing one problem at a time that we don't take a step back to actually look at the entire arena. So from the other side, we see the technological trend. There are 5 software system technological trends that are impacting everyone. I start from the promises of AI. I don't need to explain it to this community, but we know that it is to a certain level is around us. We are using it in our daily practices and try to see the application of it in many different domains. But the promise of prediction of usage of data and also analytic and AI algorithm, it really depends on the right data that you have. And this data today is not shared. So data is that I'm needing from the different actors to come together and actually give me the full context is not easily shared. So what is it that we need? We need data and knowledge services that is allowing this sharing to happen. The other area is decentralized environment that is allowing peer-to-peer solution and reducing the overhead that comes with the centralized system, but also single point of failure. But today, there is no dynamic value chain creation, and the network is actually, if you look at the network, yesterday we heard about the cloud, there are single actors really taking best care of their own domain. So what we need is the mastery of a decentralized environment. Another area is the API economy and the business service business that is everywhere. From the small business to big businesses, we are thinking about the service-based business. And we are in the network domain itself, we are familiar with the notion of network exposure, and the concept of network API is there, but we are still relying on a static or statically created services. So in a sense, hard-coded, they are already available and they are exposed, and then we are using it. So what we need is to go from static services to autonomously creating these services. Then we have an increase in the computing usage, and network cloud convergence or network compute convergence is a story that is heard across the ecosystem, and many students perhaps are working on it. We heard about the edge cloud, and we have workshops around this conference as well going on this topic. And when we see also the relevance of network in the network edge convergence, because it can play a role for the application of loading and federated learning. However, today still network and compute administrative management is in isolation. So what is it that we need? We need to extend what we call extended computing services. So regardless of where you are able to actually use those computing services. And of course, last but not the least, I started as my first use case, but coming back to that, we know that it's continued to expand, and only one example of technical enabler in this area is digital twin, seems to now be everywhere. But still, the challenge is The network and application are oblivious from each other. The performance of application is one side. We want to improve it. Performance of the network and efficiency of usage of the, resources in the network is another side. So what it is that we need network application symbiosis. So combination of all of this seems to be daunting. So if anybody is also obsessed about complex system, here is one. But is it possible to actually address all of it, or is only a fantasy? Because we want the end result to be simple and secure. So security is not something that is add-on, but it is actually part of every single system that we see here. So here comes, none of these areas actually particularly new. The new realization is, however, the dependency and correlation and importance of addressing all of them together. It has started in my own lab. Of course, as a researcher, we like to focus in one topic. And when we do our PhD thesis, we have to narrow it down. We have to scope it such that we actually can find one solution. While that is possible, when we do a theoretical study, in practice, the things actually combine, and then you see the system is not efficient. So we try to transform the challenge to the opportunity. So the hidden challenge actually behind this seemingly distinct area lies precisely in their deep interdependency and the correlation they have between each other. If you overlook this connection, any solution that we create in one area will be partial. And then we need to yet create another layer to sort the next one. The solution will be fragmented and incomplete. And we will not be able to address the whole situation and really benefit from the digital evolution. But how do we want to do that? You see, traditionally in network that were hardware-centric design in mind, we were dividing the system into different nodes, different components. Think about performance of each in isolation, and then they will combine if you have a good link between them as well. This hardware-centric design has transformed to our view when we want to actually define a software system as well. So naturally we say, let's look at each of these areas in isolation. But then we add it together, it becomes too complex and is inefficient at the end. So capturing the complex correlation across these domains requires actually a different approach, a synthetic approach. So if you take something from this slide, please start thinking instead of analytical, traditional, hardware-centric view to synthetic approach. When we take the understanding and changes in each of the node after understanding the whole system and the expectation we have from the whole system. As you see also color-coded in this, almost the three components on the bottom with the red highlighted, they are almost able to compose a platform, what we call platform that provides services, even though I see them as a flat architecture. And there is, as a software, when you go in the code, there is really no layer on the top of the layer. Again, that's a concept that is really inspired from designing hardware and network that are hardware-centric. So if you look at the three foundational layers on the bottom as a solid platform, upon that, then we can think about the API economy and autonomous services, and also Industry 5.0, which is marked with symbiosis of the network and application. And how do we grab this correlation? To go from drawing it to actually making it happen. These are huge systems, each of them, and adding them together, 5 huge systems. How could we do that? When the problem gets too big, the answer is actually very, very minute, means that it actually reaches the minute element in the network, which is the software element. So regardless of the solution that we want to have in each of this area, we see the whole thing as a combination of software elements. We envision a UNEXT native system to be an end-to-end unified intelligence system composed of collaborative agents. We refer to them as UNOP, being UNEXT operator. And this UNEXT operator work in a flat architecture. And then each of those elements carry a workload that could be part of the solution to any of those 5 areas that I mentioned. Still, they will have the same shape and format. That means they are interoperable at the root, at the design of the software, because they all have the same format. Each UNOP then is able to carry also the property from all of those 5 domains. That means each UNOP is deployable, it is knowledgeable, it is autonomous, using the intent-based mentality at the software element level, and capable of adapting itself and also collaborating with others real time. So these are the 5 properties that we got from those massive systems. We bring it down to the software elements that are actually composing the services. Then the system actually is built on 2 core design principles of modularity and decentralization. Again, this modularity and decentralization are not new concept, but using it in this context is really appropriate. Modularity then allows us to have a system that is organically formed through the interaction and the cooperation of the entities in the peer-to-peer manner, without actually having the one controller on the top. So you can say, if I have all of this software element, all of this UNOP, who's going to be in charge? Well, we are saying that there is no one in charge. Means that is actually a fully peer-to-peer system. And the second one is that actually this is distributed. So decentralization and modularity really go hand in hand in this context. Powerful software element that they can act together to form a decentralized system. So we said by design, these UNOPs are modular, loosely coupled, autonomous, adaptable, knowledgeable, and so on. And 2 concept of modularity and decentralization really allows the scalability of the system as well. Because think of those 5 big systems that we put in place. If you want to have the full solution in place and then integrate them together, then you will have a massive system that nobody is able to maintain and nobody is able to afford, frankly, as well. So then I want to go a little bit, draw the same picture in a little bit more detail, so taking a little bit of magnifying glass. The UNEXT platform, even though now I put it in 2 layers for the convenience of kind of capturing the concept, because we are still somehow accustomed to layer system. This is not a layer system, but you can see that there are 3 layers on the top or 3 components on the bottom. They are creating the solid platform, and on the top we have the enablers for the services for adaptive and also autonomous services. To start with, on the bottom left is extended computing services, which addresses the orchestration of heterogeneous network and compute capabilities along the entire device edge cloud continuum. And then for dealing with the challenges of AI, on the bottom right, we have knowledge and data services. These are the mechanism for efficient use of data and on-demand creation of knowledge and data services across the entire continuum now, right? Having this required knowledge, then we can address decentralized environment, because we have enough knowledge to actually build the trust mechanism between the different actors. On top of that platform, then is enhancement for application performance and network efficiency that creates this dynamic network application symbiosis. And also we will achieve the service creation by contextualizing, composing, and committing new services dynamically. So again, these are big missions in each of them, but in each of them, again, we have a system that we take the property of those systems, try to apply it to the different enabler in that system. So again, we take synthesis approach in each of those subsystems, if you wish. So now let me focus on one at a time. Hopefully you are so far with me, why we needed to do what we do, and also how do we envision to do this in a synthetic approach, and also taking really the transformation at the most granular level in the software element. But now I'm going to come and talk a little bit about one of these areas at a time. So what it is. Zooming on first most critical area, it's starting with the extended computing services. So network compute convergence really has many challenges. There are business issues. Yesterday also it was a talk around that, and also market challenges. But there are also systematic distinction between the compute and network. There are two isolated domains as we see them today. On one side, we have Shannon limit. On the other side, we have Moore's law. Then we say that there is an upper limit of the amount of transmitted data without being challenged by the noise in the network. On the compute side, we said there is a limit on the number of transistors, or how small we can have the transistor before we hit the physics limit. So we have even defined the limit differently. However, again, in the parentheses now, I have one of my own passion and study is really is at that limit, is there any convergence happening there? So if we take even convergence to the next level, but hopefully that's topic for another talk. We see the network performance is measured by bandwidth and latency, while compute performance is actually measured by how many functions you can do in a given amount of time. We want to achieve end-to-end efficiency, but the end-to-end efficiency, we actually really see the network in a horizontal way. End-to-end efficiency in the compute, we see it vertical from the application all the way down to the processor. So to be able to blend these two, for us as a scientific community, technology fanatics, from one side, we are coming with the distributed computing. And from the other side, we come with in-network processing and integrating more processing in the network. So we really go from the domain that we are in, and we are really capable of kind of pushing the limit and trying to go a little bit further to the other side. But what we really need to think is about the expectation, again, going back to the user and the usability of this environment. So we should start to trying to think about getting best of these two worlds, to be able to have application roaming, similar to call roaming, for which we have, for example, handoff built in the system. You don't need, as a user, you don't think about handoff. Handoff is already embedded in the system. But today, for your application portability, you have to start scratching your head on how do you actually move the things around. And on the network side, then we need much more programmability, dynamic programmability. We have a SDN controller at the switch and so on, but the dynamic programmability, real time, when something changed, can I reprogram and reconfigure the network? This is almost like sin. You can't reconfigure the network in the runtime because there are multiple users, right? So what is it again? Network compute continuum. Many times when we talk about that, we start to dilute one and then focus on the continuum from the compute continuum or end-to-end orchestration. So we can see it as a distributed computing system that is latency sensitive and is actually taking the network dynamic behavior of the network into account, and the dynamic latency for every second is different. And this distributed computing service system will actually allow the roaming of workload. And from the other way around, it could be a network now that uses its own computing capacity that is used only for packet processing to actually host the application workload as well. So that we are actually coming a little bit closer to each other. But in both cases, whether you come from left or right, we see that the span of it is from on-premise edge node all the way to telco edge and also to big data center. You can also see it as a unified management, but actually coming together now the different management system we have. So how do we envision, first and foremost, the continuum in the light of UNEXT? First, we start with the basic. This is an abstract system view of a network compute continuum, include all the functionality that is needed for this continuum to work. It accounts for distance between the nodes, the type of network that is actually connecting these compute nodes, and also heterogeneous computing that is underneath. Could be CPU, GPU, DPU, soon QPU as well. But there are common functions or orchestration, lifecycle management, and so on that needs to be in place as well. But now, embracing the UNEXT mentality of decentralization and modularization, we start also to take intent-based communication system to this level. And we see the system view of UNEXT network compute continuum by defining this different compute as different islands that are, each of them are like a decentralized environment. They are separate from each other, but they communicate with each other in a peer-to-peer manner. We can also look at all the functions that we needed for managing this continuum. Now they are UNOPs, means they have the same look and feel regardless of what is the workload in them. That means they can actually, at the management level, they can come together also. So you see, when we do transformation at the foundational level, then everything suddenly becomes easier. So this is regardless also of business model. I know there are a lot of challenges in this space about business model, but this is actually also addressing the business model. You can have any business model. There is no need for argue. You go ahead and actually compose your UNOPs to manage this whole thing in a, for example, marketplace-like environment, or if it's one operator that has both cloud and network, again, can have easier time to managing the whole thing. So I want to give one example in this space to fully harness the potential of this UNEXT-built network compute continuum. We're actually thinking about the intent-based management coming from taking into account what is the application requirement. What is the intent with this, not from the one who built it, but the one who is using it. So the application demand now comes as a graph. So you get the graph of application component and the link between them, and the requirement of application comes actually on both the nodes that are composing that distributed application and also the correlation between them. So this abstraction enables this rich, flexible mapping of application requirement into the continuum infrastructure. And also different graph realization can be generated depending on the changing requirement from the application as well. And one emerging and increasing demand this day is on the energy efficiency. And think that alongside of the processing requirement, the network latency requirement for this application, you also get the energy requirement. So we can map that to the infrastructure and the component that needs to compose those applications, and then use the information that we have from the underlying infrastructure to find the best place to deploy that application. So then it becomes that UNEXT network compute continuum is not only about blind deployment of application, but actually taking the intent of the application in mind and managing the intent even at the UNOP level. So then I come to the next area, knowledge and data management capability in this platform. And it's the core functionality. You could say, why didn't it start with that? Because that core functionality. We need knowledge to do anything, even when we talked about the extended computing services and the continuum, we needed knowledge. Yes, I had really a hard time. Where do I start? But hopefully you will see the codependency of that. And that's what I showed at the beginning. Everything is really correlated. And if you catch this correlation, then at least you will start seeing how you can capture it in your solution as well. So we said across the network compute continuum, then we already have the portability of workload, and we can take into account the graph of the application and the requirement, and we focus on the distributed execution environment, and we took into account the both compute and network, all that good. But then the shortcoming is we lack deep integrated knowledge of different domains that we traverse. We go from the device to edge of the network and so on, but we don't know the capability of them. So then it becomes a little bit abstract and not implementable, not realizable. So that means we need to add to our network compute continuum what we call knowledge continuum. And knowledge continuum also is spread across all of this domain. So embedding this intelligence within the infrastructure continuum to actually create this possibility for dynamic self-adaptation and self-optimization as well. We will come to that. And it will actually enrich the existing unified execution environment with the shared knowledge from the different entities that are participating. We need to enable, of course, seamless access, sharing of data, maybe anonymizing of the data, and also what data is used for what. We will come to that also. But this could be kind of, if I just hint to a couple of solutions in this area, this could be through automated adaptation of the format of data. So actually data is digestible. Even if it's shared, is it actually digestible? We have to adapt maybe the format of this data. But also could be that when we take into account network and compute requirement, we also take into account AI performance as well, and how the best execution environment can be done for this. But let me explain a little bit what is the knowledge continuum. We are moving away here also, the concept of decentralization, moving away from the decentralized data storage and data lake, we used to call them, and everybody started to build their own data lake that became isolated, good amount of information that they don't really share between each other. We have to go toward a system where any domain or agent can offer its own data and analytics, services, and benefit from knowledge and capabilities that other can offer. So I know that maybe the reaction in your mind is, this is not going to happen, but just hold on. I think the next topic will make it easier for you. So therefore, to realize that we really propose that enabling the extraction of the knowledge first and sharing that knowledge instead of the actual raw data sharing. So the knowledge continuum and network compute continuum, they largely superpose, but don't have always to go together. So you can actually have domain and agent that share knowledge between each other, but they don't need to build a compute network continuum. So they don't have really to be one or the other, but they can be both at the same time as well. To bring this a little bit more to reality, to make it meaningful maybe for you here as well, let me give an example. I heard from a couple of participants actually that they are working on sensing. With the 6G, we have promise of sensing embedded in the wireless network. But within any environment, there are already different sensor provider as well. So there are maybe sensor to capturing image, maybe there are sensor to capture the temperature in this room or any other alert. These data are not correlated together. So if you imagine a factory manager who needs to be immediately alerted about whatever there is, something is wrong is happening. There is anomaly in place, and there is maybe an object that should not be in place. So he needs both the position of that, which wireless sensing can give. It needs the size of that perhaps the camera can give, but also could give the temperature of it. Maybe there's another sensor that can provide that. But correlating this data, suddenly then we have a new service that could be composed runtime and actually allow that factory manager to reach what he wants. So this is basically seamless discovery and access to external and third-party data, the data that you don't have yourself, efficient reduction of unnecessary data. So you don't need to share all the data that you have from your camera, only the data that is related to this case, dynamic composition of those data, and also collaboration among those diverse stakeholders. You see each of those stakeholders contribute with certain data, but could be also contributing with the execution environment, maybe some of them, maybe not all of them. But I know before that we have to address this not so big elephant in the room is actually the reality. The real importance of the collaboration of diverse actors that each bring to the table, it really needs build-up of the trust. And this trust is not, oh, let's trust each other. We actually have to do the handshake. So if you're really serious about this knowledge sharing, let us address the relationship between them. Again, I was thinking maybe I should start with this one, because this is actually in the real life, if you want to start working with another partner, you start with the long process of handshake. Or maybe right before that, you actually share which type of knowledge you have or what is your intention. So these are all come together in the reality as well. So the knowledge that we want to share among this actor, we need to have this established trust between them, but that also means that we have to have dynamic value chain as well created. So it's dynamic trust and dynamic value chain to bring those actors together. So how we do that? There actually we go back to what we are passionate about, technology. We have trust in trustless environment. There are mechanisms for that. I will not go through them. That's not the purpose of this talk. The purpose is to show the actually dependency of all of this area together. We have zero knowledge proof, ensuring the privacy without external data storage and enabling verifiable computing. We can actually share part of the data that can be only used for one purpose. So you cannot get the knowledge or data from me and actually use it for secondary purpose as well. It can be protected to be used only for one purpose. Trust also could be about bringing, for example, devices, because we talked about continuum goes all the way to device. So device is active part of this continuum, bringing the device also together that extend really our execution environment. It's critical. We can have capability at the network or whoever who wants to host that UNOP, that actually the moment that a device is connecting, you can certify that device, whether it is trustworthy or not. So then we can actually bring to the hardware level, certify the elements that come together, and then at the software level, handshake the security. So today network contains, actually today network that we are running, they already contain some type of peer-to-peer and decentralized for some functionality. But we believe in the future, of course, as we saw the use cases, this need will go further, but also for the network itself, if we think about the multi-vendor environment, we talked about disaggregation and openness and environment that you can have different actors, different vendor providing different part of the stack. Again, you have a decentralized environment in that way. And then, even though you have this multi-vendor environment, you will have to guarantee end-to-end service performance as well. That means you need to have the end-to-end knowledge also. So all of these central challenges that needs to be addressed is to provide the quality and security that these actors can easily come together. We have key functionalities such as trust determinism, negotiation, orchestration of trustless network, if we can call that. But just to say also, we define trust as being the confidence one element has on the other to behave in a certain way. So you can have a certification that this entity is going to behave one way, and then if it behaves according to that, then it's trustable. And then if deviates, is anomaly. So again, these are technology part of it, it's doable. But then also there is more complex solution that perhaps I will not go through the detail of it, but the gist of it that is trust is a dynamic thing. That means we have to have the notion of trust resiliency as well, meaning that capability to adapt the interaction with other system across a range of trust level and also different type of assumptions. So you can have an initial definition of trust level and the reputation of that entity, but you can also dynamically adjust it. Like if you take a Uber, at the end you rate that driver, or actually I have recently seen that the driver can also rate the passenger. I didn't know that. But after you get out of the taxi, then they are actually rating you also as a passenger. So it's actually a symbiosis there also, which is really giving us inspiration. But then let me go further. With the platform now in place, we are actually starting to be able to unlock the next level of symbiosis and creating the better experience for the user. So if you create your service at the beginning with certain requirement in mind, assume you're an influencer in a shopping mall and you ask your provider to give you a network slice with certain delay and so on, but you started moving around, and then what? This is not the same functionality that you need. You need maybe more, or you need to change the condition. So what is that we are having in mind? We combine the network compute continuum, knowledge continuum, and trust. And this, we need now vertical integration, where application and this continuum stay mutually aware and adaptive to each other. So it's not that we build all of this nice playground at the bottom and then we say good luck with the application. We have to have this continuous adaptation as well. And we need to have dynamic control loops as well that intelligently optimize bandwidth, compute, and storage to align with the business level intent and also the real-time requirement coming from the user and application. And of course, we continue to have seamless communication across the diverse actors. Again, the connection and negotiation and trust, etc., between them is not one time. It has to be redone during the lifetime of this service as well. So adaptation and the continuum co-evolution, if we can call it, is all live. So the system is not a passive thing. So for that, we have come up with the notion of Stripe, a dynamically composable and runtime adaptable chain of the compute and network functions now that creates the behavior of fully dedicated environment for this service. But also it's adapting, it's like VIP service for that application or user. This network Stripe, it traverses multiple domains. Again, goes from the device all the way to the end of execution environment that is needed. When an app session is created, it uses a set of resources, and then upon instantiation of the new application session, then the Stripe establishes this path between the entity, but also the Stripe remains in contact with the application to adjust the requirement and also redo the reconfiguration that is needed. Then first is profiling of the network stripe, which converts the intent of the user to the context that it's working on, break it down to the different type of requirement that it is. Second is actually composing that component together, but also is last part is the execution over that when it's dynamically adapt itself. So if I take an example on this to make it more meaningful for you, think of a multi-object download for a web or an XR object. And this website has both this type of object is stored. And then you can see for the regular website, maybe the delay is not that critical. But for the XR object, there is another type of requirement. So if you try to take everything at the application level and try to work it out, you don't take into account the congestion in the network. So we cannot be oblivious for the reality live thing that is happening in the network, and the network condition changes. And here, if you see in this example in the picture, there is more than one network in between the server and client. If we use the default system, the XR object client will connect using a TCP, and the congestion control that is used there is either REN or cubic, and which is also best effort congestion control. Now assume your switch is part of this stripe and is enabled with L4S mechanism that's actually coming from my lab as well, and is actually negotiating one bit of EC, we call it ECN, explicit congestion notification, between the switch and the two ends of the application. So if the network starts seeing, oh, is it start to congest, start sharing those ECN with the server and the client, which are also enabled, by the way, to understand the ECN. And if they drop it and they don't act, well, they don't care, they are okay with the congestion, but if they act, they are actually sensitive to delay. So based on that quick handshake, of course, there is much more into it that I will not go through, but that quick handshake actually allows them to adapt the congestion in the network. The switch knows how to act and how to prioritize the packet coming from this versus the one that was the web. So the one that are not sensitive to delay will continue to have best effort, but the one that are sensitive, they will be a part of this negotiation. And of course, there is more in the L4S. There could be even going it at the object level, not only one session, but at the object level. Different part of this application could have different requirements. So, but last but not the least, definitely, is dynamic service composition, which aims to, well, compose the services dynamically and eliminate this prior design phase. And then it has to assure that it actually does what is promised to do. Therefore, assurance has to be an integral part of this composition as well, rather than a separate stage. So each service instance can be then, you can say, is linked maybe to a digital twin to constantly adjust itself with the reality. But also, there are a lot of more complex mechanisms underneath that makes it simple for the end user. So you have to realize that traditionally services were followed by a very linear life cycle. They started with the design, followed the creating a catalog of all of those services, onboarding, deployment, activation, and then assurance. And each of them were handled separately as well. But in contrast, then UNEXT does the observation and assurance as integral part of the service life cycle, no longer an afterthought, but also ongoing processes embed within the service life cycle. So this dynamic model is grounded again in a declarative paradigm, where the service continuously strives to maintain desired state that is requested. So some of the concepts that are very key in this area is semantic. There must be a seamless and precise match between service need expressed in the machine understandable language, but also the span from a broad spectrum from natural language processing to knowledge graph domain ontologies and so on. And then the other aspect of it is autonomy. Service must embody the autonomous behavior, means driven by learning algorithm, rules, policies, and so on. And what we have here, again, here if there is a niche here, is that UNEXT services themselves are built in an autonomous way as well. So we don't say UNEXT is a static system itself. So in a recursive way, it follows its own rule. So it's built of UNOP and also can create services autonomously. One thing that I can also say in this space is that there will be reusability of the components for building new services. So you don't have to have separated UNOPs for this, but you can have the different instance of the same UNOP for building a different services. But there are few components here. First, we have the discovery mechanism, a core resource and for the utilization of the resources here. And there is a dynamic negotiation between UNOPs, which type of resources we can actually use. And the next one is actually to instantiate the service. Another one is actually processing it and also composing it in action. And also bringing the resource and action together. So this is kind of few stage maybe in the steps that we are actually building this service dynamically. And together this approach to discovery, intent negotiation, resource orchestration, and also component reuse forms very highly flexible system for building new services. So I know it has been a lot of components, but let me put them back together in a circular way, not in the layer way. So UNEXT began with the fundamental convergence of network and compute, but it ambitiously integrates a suite of essential capability necessary to realize the full potential of the continuum and also actually address what we need in the future of the service creation in this ecosystem. So beyond connectivity and computation, UNEXT actually encompasses a holistic set of systems that make it desirable for this future that we envision for next generation of distributed infrastructure. So UNEXT, in fact, is a vision, but is also moving to realization step. You can see it as a holistic framework to enhance and extend network compute, now together with the knowledge continuum and also the context awareness and trust. And then it can foster the network application symbiosis and autonomous service creation. This all came together with the security in mind. So the build-up of the UNOP is secure, but also binding the UNOPs together for a security solution is possible. So one of the intent of the application or user could be security as well. So when we talked about network compute convergence, you can see here actually convergence of 5 different areas. Not only that, network compute convergence was one, but then we are convergence of AI with that, services with that, and so on. So what we achieve by design in a technological space, so we push the boundary by achieving simplicity through modularization. All the software elements follow the same design rule. And this will allow interoperability. So if you see, we have massive standardization organization to secure or ensure interoperability at the interface level. But for the interoperability at the software level, we come to that. We achieve security by design, as we mentioned. So in the future, we envision the migration. So we don't assume that everything that is in place will be wiped and then we can build a UNEXT native system, but you can slowly move from centralized to decentralized control. You can move from single actor to multi-actor, and you can start embracing the openness and disaggregation slowly. So you can start from the greenfield. When you are building the new system, you start developing UNOP and start digging into your existing system and see where can you transfer them to UNOP to come to more UNEXT native system. The question comes also, what is the business value? Is not that everything is just for the sake of exploration. There should be business value as well. We expect the built-in resiliency, built-in intelligence, and also end-to-end protection. So embracing all of these components, we can see actually network itself could become an operating system. We talked about the operating system as well. Who is there, where it is there. Any UNEXT native system can be seen as an operating system, but also the network itself, when it embraces all of this principle, it transforms a global operating system. Well, network is global to begin with. It is also an end-to-end system security solution, invoking all the right security solution, binding them together for identity management, data protection, access control, and so on. We see it as providing green solution because now you don't have a bulky, big solution, but you actually have all the things that only you need for that context. And also with this, we can actually build a scalable, composable, customized platform for different contexts. So if you go to a factory for car manufacturing to another environment, you can also have a specialized platform. So let me summarize at last. Really, for meeting expectation of services across ecosystem in the next era, we can take inspiration from the way operating systems were created. We can go beyond the network compute, convergence, and integrate robust knowledge continuum and also dynamic trust in there, and bring heterogeneous execution environment belonging to multi-actor. We can lay a path for open, green, simple and secure playground for innovation. And this will be a transformative impact on industries and all the other public sectors. And all of this will power the future of autonomy and dynamicity in service creation. A future that is really exciting to build and everyone can thrive in. And with that, I thank you for your attention and I give the control back to Chair.